So, about 15 years ago, I was set a problem by one of my professors at university, and it has driven me crazy for a very long time. I think I've finally come up with a solution, or at least something that's workable, and I wanted to test that out, and I'm going to use Rust. So this isn't the prisoner's dilemma as it's commonly called, but it is a dilemma for prisoners, so that's why I've given it the track. There are 10 prisoners, and the prison warden sets them a challenge. He shows them all together a room with 2 switches in. Each switch can either be on or off. This will be their only mechanism to communicate for the rest of the challenge. Once he's left them alone to come up with a plan, he's going to send them into separate prison cells, and then randomly, with no guarantee on how much time between these visits there's going to be, he will choose one with a fair random and take them to the room, and they can adjust the switches, and then they must go back to their cell. He will continue to do this, picking one at random each time. There are no guarantees about picking the same person twice or anything like that, but he would only that the random will be fair. So each time he'll pull a name out of the hat and put that name back in the hat, as it were. Once any prisoner believes that every other prisoner has visited that room, they may say, "I believe every other prisoner has visited this room." If they are correct, all the prisoners will be free to leave. If they are incorrect, all of the prisoners will remain for life. The prisoners are given some time together to come up with a plan for how they are going to use the switches, and then separated. Can we find a system that allows the prisoners to guarantee, or at least near enough? It's impossible to completely guarantee this. But can they come up with a system that allows them to get something close to certainty without wasting visits? So because obviously they don't want to stay there indefinitely. So what system can they use to do in as few visits as possible, get as high a guarantee as possible? The challenge was given to me, can they get a 95% success rate should this be repeated? So I've created a new Rust project, and I am going to define a test. So pub fun test. Now this test will take an and mute slice of p for prisoner, and it will return a result, a u size for the number of tries, whether or not they fail. And p will obviously be prisoner, and we will define that trait shortly. Well, let's define it now. So pub trait prisoner, and a prisoner must have a function called visit. And this will take our 2 switches. Now we can store this as 2 binaries, because anyone knows that 2 switches can represent any number from 0, 1, 2, or 3. So for the sake of a bit of ease, I'm actually going to use a U8. Ideally, we would use a U2, I guess. But whatever, with or without U2, we can make this work. We'll just use the modulus on U8, and that will fix it. So this will be and mute on the visit, and this will return a boolean for whether or not they believe everybody has been in that room or not. Let mute sw equal 0. We don't really need the I here, do we? So for underscore in 0 ... We'll put 1,000,000 here, just so that it will actually run out. So if the prisoners never ever choose to leave, this function is still going to end. So here we need to choose a visitor. So I'm going to extern create rand, and we will use rand and rng and thread rng. For every prisoner, we're also going to need to be able to check whether or not they have visited the room. So we'll need a tracker vector for that. So let visits equal, and we'll use vec, and we'll do it with capacity, and we'll choose that as, and this is prisoners, right? So we'll use ps.len. An optimization that may not be completely worth doing, but we now need to go for underscore in naught.ps.len, and that's visits.push 0. He will then call a visit on a particular prisoner, so he's got to choose that prisoner. So let n equal thread rng gen range, and it's 0 to ps.len. So we need to mark that this person has successfully visited, so we'll put visits at n plus equals 1. Then we need to call the appropriate visitor's visit method, so we call ps at n dot visit, and we got to send the switch, that's unmute on sw, and if that result is true, we can break this. It feels kind of funny using a counter variable here, but I don't think we can use it after the scope anyway. So here we'll have let mute I equals 0, and that's for how many visits they've been, and we'll I plus plus that in here. I plus equals 1. And we do want to check as well that no one is cheating and trying to send more than 3 out of the variable. So if is greater than 3, let's just return a fail. That way no one will want to cheat, will they? So return error, and the guess will be whatever I is. Once they break, we are of course going to want to check whether they have all actually visited the room. So for v in visits, and we can just loop through that because we don't need them after this. So v equals, if v equals 0, then we have a failure, don't we? So we'll return error of I. Otherwise we can return OK of I. So that's the success, where they have actually all visited the room. So before we can actually run this test, we're going to need a prisoner. So pub struct, we'll call it plan1. So that is the prisoner with that is all of the prisoners sharing the following plan. Have a visit count for the prisoner. One of the few things a prisoner can keep track of is how many times they have visited the room. So we'll keep visits to, and that will be a U8. And that's just to make things a bit easier working with the switch number. So we'll impl, let's give it a new method. And this will return a plan 1 whose visits is 0. And the other thing we're going to need it to do is implement prisoner for plan 1. So we'll need to implement the function visits and this will take a mute self. Ah, I missed that in the prisoner thing, didn't I? So SW for switch, and this will be mute U8. So here is the solution that I've finally come up with. As I said before, we can represent numbers from 0 to 3. So the prisoner will always put in the lowest of the current value on the switch plus 1 because it needs to increment, or the number of visits they've already had in the cell. And I was going to be this visit, but actually that leaves no space to actually use the 0 value. And you really want to use all of the values you've got on the 3 switches. So we're going to go the number of visits they've had in the cell before this one. So we'll just do a -1 on their visits. First thing, self.visit plus equals 1. So we've had one more visit now since we got here. If the switch, and we have to dereference it, so if switch is equal to 3 and our visits is and self.visits is greater than 3. In that case, we can return true, and we are going to try and leave the cell. And we believe that everybody has visited. Otherwise, we need to work out what we are going to set the switch to. Let's pull this visit count down after the switch. We're working with unsigned numbers, and we really can't handle negatives in this case. So we need to make sure that our numbers do stay positive. So we got a couple of choices for our options here. So I'm going to create a new variable to help us work out what our visit count will be. So we'll do let v equals self.visits -1. We'll do that for now. And we said we were going to compare that to the switch value, which incremented already, and then take the minimum of these two values. So switch plus equals 1. And then we can do switch equals, and again we'll dereference it, so switch, and this already has the method min, and we can compare that with v. And obviously we can't let that go above 3, so it has to be the lower of that and 3. And here we can return false. So here we have a plan for our prisoner. If the switch is at 3 and our visitors and the number of visits we have had to this cell is bigger than 3, we say, yes, I think everyone has come. Otherwise, we increment the switch and we increment our own visits. And we set a value to switch, which is switch plus 1. And then we take the minimum value of the current switch value plus 1 compared to v, which is 1 less than our current visit count. And again, it can't be bigger than 3. Now, practically, this means if 3 other people have visited the cell, then that will be enough for us to make our guess. And we cannot guarantee. If there are 100 prisoners, how are we going to guarantee how many of them have come to this room or not? We really have no means of checking. And I guess this is why this puzzle has bothered me for so very long. It's not quite as good as a solid mathematical proof, but it should come close. Okay, finally we'll write our test, and we'll just do that in the main function. Let v equal vec, and then for I equal 0 dot dot, is it in? We'll do it with 10 prisoners, that was the original number. We would v dot push and 1 new. Let r equal test on and v, and this should be a result, so we'll just print that out, and obviously it's the result implements debug, so we can handle that way. Let's try and run it. I'll debug it as we go. Oh, no crate rand. Okay, tab edit dot cargo dot toml, and of course we need to use rand equals, and it's currently 0.5.5. There we go. Errors. Expecting a colon here. So switch. Oh, I called it SW. And that's D there. Did I mean print line with a exclamation mark? Why, yes I did. And types differ in mutability. Well, actually we do need to be able to change those things, so this is mute on V. Got a new set of errors. Obviously I'm going to change visits because I need to add things into it. Yes, it really does. Done. Okay, 37. So that means 37 visits, and then they said, yes, we're okay, we're going to leave, and they were okay. That's a good start. Let's get rid of that that I there. What line is that? 77. Okay, try again. 32. Error, so they left one early there. Error again. Okay, that's not going as well as I had hoped. So sometimes they make it out. Certainly not a guarantee though, and that is not 95%. So we have a couple of options here. Actually, let's make this test more test-like. Running it once just doesn't feel enough. So let's for I in 0, 100, and that's to here. If we create fail equals 0, that should be mutable. Success equals 0, again that should be mutable. And finally let mute tot, and that's the total number of actual visits, equal 0, and then we can match against R, and if we have an OK, tot plus equals, ooh, that's a tot plus equals V, and success plus equals 1. And let's actually print out the thing as well. Print line success, and we'll print V there. And on an error, which also returns value, we tot plus equals V, fail plus equals 1, and print line fail again with V. We'll pull this out and put it here, and success fail, and then we'll have an average suck fail, and that was tot divided by, and we did 100 tests. So now if we run this in theory, so 100 is not a function. Fails plus equals 1. so there we go. We got 61 successes, 39 fails. So that was pretty close, but definitely not a guarantee. And notice their average number of visits is 30, which I think is quite reasonable. I do feel like it's close to 30 that should get you a success. And even according to this, 31s are getting successes, 25s are getting successes. But none of the guys can actually know how many other people have visited, so there you go. We got a fail at 26, so there's no guarantees even at 26 that it works. There was an I that was unused as well, I noticed, so let's get rid of that. So are there any ways we can make them a little bit more cautious but without completely undoing the entire plan? If we increase the number of visits they need before they start putting any on the switches, so you just say, well, I don't actually tick the switch until I've gone at least 3 times, right? So we can do that with this thing here. So let v equal, and if self.visits is less than 3, then we're going to put 0, otherwise we can output that. So if the visit number is less than 3, then we just don't, then that means the v will be 0 and the minimum switch value will be 0. Otherwise we put on the switches, we put -3 actually, so we just don't put anything in the switches for the first 3 values. This should mean that everybody is significantly more cautious, but there's still no guarantee. But we can only really check with the last 4 visits because you just don't know what else has happened in that time. So minor change, that gives us 87% chance of success. That's better. Run that again. 82. It's not good enough, is it? How many are they guessing? They're waiting 43 visits now on average. So it's a bit longer, much higher success rate, but it is a significantly longer wait. If we shunt this, especially remembering that sometimes 30 is enough visits, but if we shunt this up to 4, we might still do better. 86, 94, that's better. And if we shunt this up to 5, well, obviously we can make this number higher, but this is really a challenge of optimization. How many do we actually want to wait? So they all passed. Oh, 2 failed. They're averaging at 68, so we got a fail at 36 here, so someone actually made it through without someone else. We got a fail at 48, so it is possible for someone to last with 10 people to have 48 total visits and 1 person not chosen. So there are some challenges. Are there any ways we can make this better with extra checking? What about, let's make a new prisoner, a new plan. So we'll call let's just copy and paste this code, because who wants to write that twice? And this will be called plan 2. And this time we're also going to need a highest on the highest it's ever seen the bar, because it's not going to put it more than its highest either. More than its highest plus 1. So obviously its current highest is 0. I think actually we can get away with copying and pasting this code. So we'll pull this back maybe down to 3. So we also now can remember the highest thing we have seen. So that means we can put in a check for another 4 people, I guess. So we go and self.highest is also equal to 3. So it's not going to do it if it's not seen a 3 before. So he's got to have seen a 3 twice to count this as a successful run, which should in theory mean maybe 7 people have to have seen that mark. And here we can also min that with self.highest plus 1. Oh, I changed my mind there, and actually we're going to increment the self.highest at this point here. So this becomes if SW is greater than self.highest, we will set self.highest equals SW. And this is implementing this for plan 2. And if we want to run this in our test, obviously we're going to need to change this to create new plan 2s. And now plan 1 of course won't be used anywhere. Attempt to add with overflow. We can never increment SW this way, so I think we may need to put a plus 1 there. So yeah, that was the visits overflowing because it was visiting but never succeeding, and so this is still also failing at similar numbers. I guess we can set this back to 4, and that will probably get us a better general result. "98 successes, that's 95, and our guesses can still come down. A success at 42 there was our highest fail, is 43. Yeah, I feel like 57 you really ought to have found a successful run. So some combination of these, we are at least getting above that optimal number. I guess you got to fiddle with those numbers that the guy gets to keep to get the perfect result. I know you can get it if you put this number really high, like 8. It will not fail, but they're averaging 103 guesses, not in the 50s and 60s, so that'll be the reason. Anyway, I hope you found this puzzling through a little bit interesting. Either way, feel free to like and subscribe or do all the usual things. I'll see you sometime in the near future.